Hey, so we're going to go a little bit home movie here style, a little bit of selfie style for our lab today. So I'm going to take the measurements, and our goal is going to be for you to extrapolate out and figure out what temperature, experimentally, absolute zero is. So absolute zero, of course, is the coldest possible temperature, and it's really defined as the temperature at which all molecular motion stops. So normally atoms, atoms and their components, the protons, neutrons, and electrons are moving around, they're wiggling, they're jiggling, they have some level of internal kinetic energy. At absolute zero, temperature is so cold that motion stops. And it's kind of a theoretical temperature, but we can actually figure out through graphing and through experimentation what that temperature would be in Celsius and Fahrenheit. So to do that, to do this demo, we're going to need a couple things. We're going to need a cold water bath, which I'm going to prepare, a hot water bath, an Erlenmeyer flask. Here is our Erlenmeyer flask. We're going to need to know its volume. So to figure that out, I have my graduated cylinder here, getting my hot water bath set up there. That is coming up to temperature, and my cold water bath, I have a bucket, I have a bag of ice. It's over there. You will see that as we go through. So I'll also need a temperature probe, which I will get out. So that's what we're going to do. I'm going to give you a couple volume and temperature points using what we know about water and what we can measure. And then from there, your job is going to be to actually make a graph. You can use Google Sheets or Excel or numbers, or you can do it by hand and extrapolate out what temperature in Celsius is absolute zero. So our first step here is going to be to figure out the volume of this Erlenmeyer flask. Now, it says 125 milliliters on it, and that's certainly a great unit to use, but I need the volume of all of the air in it. So how much volume is going to basically be up to that stopper, because I'm going to need it to be airtight. So to do that, it's really hard to measure air, so I'm going to fill my flask here all the way up to where that stopper is going to be. Oh, a little more. So if I'm remembering, so I put this in, pushing out the extra water. Maybe a little bit less here. Tiny little bit less. Helps if you see things, I suppose. Alright, that's really, really close. I'm going to add a little bit in. So I think I was actually on the right track the first time when I let the stopper release what was extra. So we will see if we can get that again. Yep, so anything extra has now flown out, so I have an Erlenmeyer flask full of water. Now, if I can figure out what the volume of the water in there is, then I'll have the volume of the entire flask. And that's where my graduated cylinder comes in. I'll go ahead and pour carefully all of the water in. I think I'm going to be over my 100 milliliters here. So 100 milliliters of water. Don't need it, I'm just using it for measuring purposes. Get all the way out of there. Plus, try to get all the water out. We're going to be pretty close here. Plus, of course I'm on the backward side, plus 10, 20, 30, we're going to say 39. So the volume that I'm going to use for my Erlenmeyer flask here is 139 milliliters. Okay, so good news is that my water here is boiling, And I can take the temperature of that, which I'm going to hope here is pretty close to 100 Celsius. 98.5, 98.7, 99, 99.3, and then 99.4. Of course, water boils at 100, so 99.6, 7. We're going to call that 99.7 Celsius. So what I'm going to do now is submerge my beaker. I'll show you here in a sec. So I submerged the beaker into the bath. Now the beaker is filled with air, so I'm just going to let it sit in there for a couple minutes. Goal here is to get the air in the beaker to come to the same temperature as the water, so that'll be our 98.7. So we'll give it a minute and then check back in. All right, we've been boiling away for about a minute here, actually about 4 or 5 minutes. So I'm going to hope and approximately assume that the temperature inside my flask is pretty close to that 99.7 degrees. Thermometer's getting tired on me, might have to grab a different guy. What I'm going to do now is I'm going to use an oven mitt. I'm going to put my stopper into the flask so that I can contain just the hot air in the flask. Then I'm going to take it out from the hot water bath and set it on the table. And I'm going to try to prop this up and hopefully you can see at least some of that. Very hot, so I don't want to touch it. Certainly not with my bare hands. I'm going to release the clamp, so I just have Erlenmeyer flask. Fortunately, rubber's a good insulator, so I feel like I have a pretty good seal. I'm holding this and I'm going to let it cool off. So I'm going to let this air come down to room temperature but stay in the Erlenmeyer flask. Okay, I have allowed this to cool. So my next steps, I'm going to take my flask, good and sealed, turn it upside down. I'm going to invert it into the water, just with the cap on. Well, it's upside down so that no other air can get in the water. I'm going to take the stopper out. Some water is going to get sucked up as the colder gas, as the gas cools, it's going to compress, so it's going to cool off. I'm going to hold that in there for 4 or 5 minutes and then bring the flask up so that the surface of the water in the bucket in the ice bath comes up and matches the surface of the water inside the flask. I'm doing that to make sure that the pressures are balanced and there's no extra pressure effects. And like I said, I'm going to hold it there for 5 or 6 minutes, and then I'm going to check the temperature of the ice bath and assume that the air inside my flask has come to the same temperature, and then we'll move on to our next step. Alright, so had my flask here in the ice bath, and yes, it is very cold. It's been about 5 minutes, so what I'm going to do next is take my stopper, wherever I set that guy down, and then I'm going to carefully, like I said, balance the water level in the flask there with the water level on the top. While doing that, I'm going to replace the Erlenmeyer, or the stopper in the flask, and then I'm going to take it out and move on to the next step. Alright, so having taken the flask out, put the stopper back in, now I have some liquid in here. What I want to know is how much air is in that stopper. Remembering that there were 139 milliliters in the stopper to begin with. I'm going to pour the water back into my graduated cylinder, measure that, and then I'm going to do subtraction to figure out how much air is in the Erlenmeyer flask. Just double check on the temperature here. My ice bath, because this is what I'll be using. 2.6 Celsius, 2.5, 2.7. Pretty cold. Let's say we got our water down to 3 degrees Celsius. We'll use 3 degrees. So 3 Celsius is our cold temperature, 99.7 is our hot temperature. Let's find out how much air is left in this flask. Almost missed and ruined everything. So there were 41 to 42.8 roughly milliliters of water in that flask. So let's go to the board and then do some math. Okay, so let's walk through the math here. So at 99.7 Celsius in our hot water bath, we had a 139 milliliter flask, which had no water in it and then some amount of air. Of course, since there was no water in it, the volume of the water, or volume of the air, was 139 milliliters. Now in the cold water bath at 3 degrees Celsius, we had 139 milliliters possible in the flask. 42.8 were filled with water, so I needed to figure out how much was filled with air. That's just algebra, subtracting 42.8 from both sides gives me 96.2 milliliters of air at 3 degrees Celsius. So now, the things for you to do are to make your own data table, which should look something like this. We've got temperature and volume as our two variables. So there's a hot point, which is 99.7 Celsius, 139 milliliters. Cold point, 3 Celsius, and 96.2 milliliters. And our question at absolute zero is, what's the temperature in Celsius of absolute zero using our data? So that would be when the volume is zero, because at that point, all of the air would have condensed down to essentially be a zero volume. So you need to, 1, make a data table, turn it in. 2, make a graph, turn that in. And 3, using the graph, extrapolate back to the value of absolute zero in degrees Celsius from the data, not from Google. Good luck. Email me if you have any questions.